So this is lecture 3, example 5. And it looks a bit different to the other examples we've been considering so far. So let's consider an defined to be equal to square root of n plus 1 minus the square root of n. So we can have a look at that. We've got it here. And you can see that it's getting smaller, 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 and it does seem to be tending to 0. So we conjecture that an tends to 0 as n tends to infinity. And we want to prove it. So we want to make it fit the pattern. For all epsilon greater than 0, there exists a capital N, possibly a function of epsilon, element of the natural numbers, such that if little n is greater than capital N, then the difference between the nth value of the sequence and that conjectured value of 0 is less than epsilon. Now we want to prove there exists n. So the way to do, a very nice way to prove an exists statement is to make an explicit construction. So we want to choose capital N of epsilon to be equal to something. But maybe I don't know what that something is. If I haven't looked at an expression like this before, I won't necessarily know what to choose. So here's a thought. Instead of writing this down, what I'm going to do is imagine I've written something down there, blah, 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 whatever it is. And I'm going to do the calculations that I would do had I written something down. And then I'm going to use that to try and guess what I should write down. So let's consider an minus 0 in absolute value. This is the square root of n plus 1 minus the square root of n minus 0, which is just the square root of n plus 1 minus square root of n, because square root of n plus 1 is always bigger than the square root of n, so that thing's always positive. And I look at that and I think, oh, I don't know, what does that mean? Experience with math says that when you've got a difference of 2/3, a useful thing to do sometimes can be to multiply by 1 in the following form. I'm not changed anything, because all I've done is multiply by 1. When I do that, I multiply out square root of n plus 1 by square root of n plus 1, that's n plus 1, plus something minus the same something minus n, all divided by square root of n plus 1 plus square root of n, which is 1 divided by square root of n plus 1 plus square root of n. And you might say, well, so what? You've just replaced some ugly difference with an ugly sum, this time in a numerator. But actually it's really handy to have something in the numerator, and I'll show you why in the little aside over here. Aside. Square root of n plus 1 plus square root of n is greater than square root of n plus square root of n, which is just twice square root of n. And that means that 1 on square root of n plus 1 plus square root of n is less than 1 on 2 square root of n. And now we've got a product instead of a sum, which is really nice. So I can write less than 1 on 2 square root of n. Now I want to do a chain of reasoning that says this is less than epsilon. So here comes my second aside. I want 1 on 2 root n to be less than epsilon. Well, that'll happen if and only if, let's square both sides, 1 on 4n is less than epsilon squared, which in turn will happen if and only if 1 on n is less than 4 epsilon squared, which will happen if and only if n is greater than 1 on 4 epsilon squared. So that tells me now what my guess has to be. Let's choose 1 on 4 epsilon squared, except I've got to round down to make it an integer and add 1 for convenience. If I have made the choice capital N is equal to this thing here, that implies that whenever little n is greater than capital N, it will be greater than 1 on 4 epsilon squared, which means that this, working backwards, implies this. And so indeed we have the inequality that we desire, and we are done.